The hyperbola. All right, so in this video, we are going to look at the definition of the hyperbola in relation to its geometry, not its cross section. And then we'll look at the formula for the hyperbola. We'll derive the formula in this video, which is something that you don't always see. And then we'll look at variations on that formula and do some examples. But without further ado, let's go ahead and get started. The definition. The hyperbola is the locus of points such that the differences of the distances to the foci is constant. So let's make sense of that. To do that, let's go ahead and define some things in this picture over here. This is the hyperbola. So B and A are our foci. Right? The hyperbola is going to have two foci, A and B. All right, and the differences of the distance from this foci to the hyperbola and then to the other foci, the difference between those two distances is always going to be constant. So I have this point over here, x, and I want to look at the distance bx and the distance ax. Right? That is some number. Right? And when I say the difference, I'm going to go ahead and call it the absolute value. So that I don't really care about the sign, the SIGN. So AX minus BX, right? That value, no matter what point I pick on this hyperbola, whatever this number is, that number will always be the case. If I pick a different point, for example, Y, down here, if I pick this point, right, the difference AY and by, ay minus by, right? X and y are two arbitrary points on this hyperbola. Though the difference between these two values will always be the same. These two things are equal. So A and B, the foci, they kind of define this shape. I can arbitrarily choose where they are, and then the locus of points, these two darker lines, is the hyperbola, and it is determined by the foci. So that's an important term, the foci, two arbitrary points. Let me go ahead and write that down. So the foci, two arbitrary points. All right, but some other important terms that come along with this, we have the center here, E. All right, how can we define this? Given all we have are the foci, the center is going to be the midpoint of points A and B, of the two foci. Here we are calling this point E, the midpoint of A and B, E. All right, the hyperbola also has vertices, just like the ellipse and the parabola. So here we have C and D. All right, C and D are our vertices. And the way we're going to define those also is going to be using the foci. If you connect the foci with a segment, where that segment intersects the hyperbola are going to be our vertices. So let me write that down. Where the segment made by the foci, I'm running out of room here, intersects the hyperbola. Right, that's going to be our definition of the vertices. And so I've run out of room here down at the bottom, but I'm just going to write this last term over here. We have something called the transverse axis. And that is defined as the segment with endpoints, the vertices. So the segment constructed using the vertices. All right, so like what created this hyperbola? The foci. The foci are really the only thing that matters, and then all the things that came from that, the center, the vertices, the transverse axis, all are dependent on where those two foci are placed. All right, I'm about to go to the next page, and we are going to take a look at the relevant numerical values, all right, the distances that we care about that help us construct this conic section. So here we go. To do this, we are going to center our hyperbola at the origin of the Cartesian plane and then go from there. So for example, the length between the center and the vertex is going to be A. All right. So the length, it's going to be a positive number. So this is also A. All right, the length between the center and the vertices are going to be A. So we can say that the length of the transverse axis, the length axis is 2A, and that number is going to be a little bit relevant later. All right, the distance between the center and the foci, we're going to call that C. So the distance, or I guess I'm going to try to be consistent, the length from center to foci is C, thus making the coordinate of each foci C. So this length right here, that is going to be C. Similarly, this length here, that is also C. The left one is going to have a coordinate of negative C. So I have an exercise for you. And I'm going to do it right after I claim or I describe the exercise. So go ahead and pause the video after I write this down. But I want you to determine the constant difference in terms of things you know. What is the constant difference that defines this hyperbola? What is the length from foci or focus 1, and I'll call B focus 2, I'll just call them A and B. What is the constant difference? AX minus XB. What is AX? This length right here, not the straightest line, sorry, minus this length right here. What is AX minus XB? What is that length? I'm putting absolute value. This will clearly be a positive number because AX is longer. But if I had chosen a point on the left, what we call branch of the hyperbola, AX minus XB would have been a negative number. But I want that to be a distance, so I'm going to go ahead and throw absolute value bars around it. So finding that difference currently is impossible because we don't know this point x. It's arbitrary. But we do know some points on this hyperbola because of the way we have added coordinates to our system. Right? C and D, the vertices, are on the hyperbola. And the constant difference is always the same. So a good thing to do to solve this question would be to choose a different point, C or D. You know what? I'm going to choose D so that AD minus DB, it should be the same as AX minus XB. That's the definition of a hyperbola. That distance should be constant. So what is the distance AD minus DB? What is AD minus dB? These two quantities, as stated by the definition, should be equal, and this bottom one is we can calculate it. Right? The length AD, or so let me rewind. The length AE is C, and the length ED is A. This is the segment addition postulate at work. AE plus ED is AD. I'm actually going to break that down. Let's go ahead and do that. AD is congruent to the segment AE plus ED. And then we're subtracting DB. Similarly, using, once again, the segment addition postulate, DB, that's going to be EB. This is EB. So let me go ahead and write this again. Right? DB minus is EB minus ED. All right, and let me carry this over. We have AE plus ED. Things are going to cancel. All right, ED and, so that doesn't cancel. ED minus negative ED, that's 2ED. The things that actually cancel are AE and EB. AE is C, and EB is also the length C. So this is the length C. Let me go ahead and translate these. This is C and this is C. C minus C is 0. ED is A, and ED is A. So we have the quantities C plus A minus C plus A if I distribute this negative. Right? The C's go away, and I've run out of room, so I'm actually moving up the screen. The length between, the constant difference between the hyperbola and the two foci is the value 2a. The length of the transverse axis, 2a, is actually the constant difference that defines this hyperbola. All right, so that value a, right, the distance between the center and the vertex is a very relevant number. It determines this hyperbola. Let me just say that one more time. The constant difference that defines this hyperbola is the length of the transverse axis. All right, let's derive this thing. It's a doozy. All right, so what do we know? We know that the constant difference is 2a. That is critical in doing this derivation. So we need to choose an arbitrary point on the hyperbola. I have the point P right here, right? And the distance from foci to point P. And then subtracting the difference from point P to other foci, right? The difference, AP minus BP. AP minus BP, right? The length must be 2a, where a is a positive number in the right direction on the axis. Right? This is true. All right, and since we have an arbitrary point here, x, y, we can determine what AP and BP are because we know the point A and we know the point B. So go ahead and write down what the length of AP and BP are given the point x, y. To make the algebra easier on me, I'm going to assume that AP is larger than BP. It is in my picture. I'm going to derive the right-hand branch, but you will see if you choose to later switch BP and AP, you're going to get the same formula. So I'm going to go ahead and just drop the absolute values once again to make that algebra a little bit more simple. All right, so AP, that is the distance between negative c comma 0 and x comma y. We have x2 minus x1, x plus c quantity squared, plus, what is that going to be? Y minus 0 plus y minus 0 squared, all square rooted. All right, the next value of BP, that's going to be, I'm going to go ahead and write the 2a now. That's going to be x minus c, quantity squared, plus y minus 0, also just y squared. All right. All right, technically, I have the right-hand branch of a hyperbola formula right here. The goal here is going to be to clean it up. I made a Desmos of this right branch. So we have that formula a little bit peeled off here, equals 2a. But give me an arbitrary value c. What is c? The length between the center and the vertex. The center and the focus. And then if you give me a length between center and vertex, a, then you're going to get a, there we go. Or you're going to get the right branch of a hyperbola. You can play around with the sliders. All right, I'll post this later if you want to play around with it. But the point I'm trying to make is we currently have the right branch of a hyperbola. If I had switched the order, I'd have the left branch. All right, so let's clean it up. I challenge you to do this. Go ahead, pause, and try to make this into a nice, beautiful formula, one that emulates the circle and the ellipse if possible. What I'm going to do is I'm going to add this to the other side so that I have lots of positive things, and I'm going to square. It's going to be a little bit nasty, but we've squared square roots before, so we should be fine. All right, we have the square root of x plus c squared plus y squared, and that's going to be equal to 2a plus the square root of x minus c quantity squared plus y squared. Let me drag that over. Cool. And then now we are going to do the worst thing in the world in algebra, in my opinion, and that is square square roots. So let's square both sides of this equation. The left-hand side will be x plus c quantity squared plus y squared. And then the right-hand side is going to be 4a squared, right? A squared plus 2ab plus b squared, right? That is our binomial square. So for a squared, then we'll have plus 2 times 2a times the square root of x minus c quantity squared plus y squared plus, and then x minus c squared plus y squared. All right, we just squared both sides, and we don't want to forget this 2. That's often forgotten. All right, we have the first term squared plus 2 times the 2 terms multiplied plus the second term squared. This is more complicated than the previous line, but we have one less square root. So what we're going to do is we're going to do that one more time. Let's get rid of that second square root. The new square root. All right, so I'm going to move everything but the square root to the left-hand side. I'm actually going to do a little bit of cleaning up along the way, and then I'm going to square again. So I have x. I'm actually going to expand this here. X squared plus 2xc plus c squared plus y squared. That's the current left-hand side. But I'm also going to subtract 4a squared, and I am going to subtract, all right, x minus c squared plus y squared. All right, you know what? I'm going to be do a little bit more work than I normally do. I'm going to not expand this yet. I'm going to expand it on the next line. And then this is going to be equal to 4a times the square root of x minus c quantity squared plus y squared. Oop, I caught a mistake. This shouldn't be a plus. The way I'm going to resolve that is just throw some parentheses right there. All right, now expanding this parenthesis here, I'm going to get x squared plus 2xc plus c squared plus y squared minus 4a squared. And then I'm going to have x squared minus 2xc plus c squared, but all subtracted. So I'm going to have minus x squared, right, minus negative 2xc, so plus 2xc, and then I'm going to have a minus c squared, and then a minus y squared, and that's all going to be equal to 4a times the square root of x minus c squared plus y squared. I could expand this, but I'm not going to do that yet. All right, I ran out of room, so here we are on the next page. Some things are going to cancel, right? The x squared minus x squared, boom, they're gone. The 2xc plus the 2xc, that's going to become a 4xc. We have a c squared minus a c squared, gone. Right? We have a y squared minus a y squared, gone. All right, we have a minus 4a squared. All right, so we accounted for this. We accounted for this, and we just accounted for this. Cool. All right, this is the left-hand side. A lot of things disappeared. On the right-hand side, we have a 4a square root x minus c squared plus y squared. So things are getting kind of nice. Let's get rid of these 4's. Divide both sides of this equation by 4. So we'll have xc minus a squared is equal to a times the square root of x minus c squared plus y squared. Cool. All right, we're on our way to getting a nice, beautiful formula. Let's go ahead and get rid of this square root. How do we do that? We square both sides. All right, so squaring both sides, we are going to get the left-hand side. You know what? I'm going to be a little bit slow about this. I'm going to rewrite it all out. And then over here, I'm going to get a squared. And then the square root is now gone. That was our intention. All right, some of these parentheses are not necessary. But actually, no, they're all necessary here. Yeah, because the a squared is going to distribute. All right, cool. So over here on the left-hand side, we have xc minus a squared quantity squared. So the xc is going to become x squared c squared. Then we're going to get a minus 2 xc a squared. And then we're going to get a plus a to the 4. Over here, we're going to have a squared. And then I'm just going to go ahead and leave it for now, x minus c squared plus y squared. All right, let's go ahead and now distribute the a squared and then see what gets canceled out. Okay, so the left-hand side, we're going to leave it for now. The right-hand side, we're going to have x squared minus 2xc plus c squared. So we're going to have a squared times x squared. We're going to have a squared times negative 2xc. And then over here, we're going to have a c squared times a squared, so plus c squared a squared. All right, this is just x squared minus 2xc plus c squared, but the a squared has been distributed, so a squared, a squared, a squared. This a squared's in the back for some reason. That's just by accident. And then we're going to have a squared, y squared. Cool. Let's see what disappears. Only one thing disappears. It looks like that's going to be the 2xca squared, but that thing is pretty nasty, so I'm glad that it's gone. We have a negative 2xca squared on both sides of the equation. So what does this look like? We're going to have an x squared c squared plus a to the 4th is equal to a squared x squared plus c squared. You know, I'm actually going to put the a squared in front. A squared c squared plus a squared y squared. There's some factoring that can be done here. All right, what do I want to do next? I want to move everything that's an x and a y to the left-hand side and move everything else to the right-hand side. Why? I have this goal of turning it into something that looks like the ellipse and the circle equations. So those have the x's and y's on the same side. So I'm going to do the same here. So I'm going to have an x squared c squared. I'm going to move the a squared x squared to the left-hand side. I'm going to move the a squared y squared to the left-hand side, and I'm going to move the a to the 4th to the right-hand side with the a squared c squared. All right, so let me just double check that I haven't dropped anything. We have the a squared c squared, the a to the 4th, we have the a squared x squared, yep, we have the x squared c squared, and we have the a squared y squared. So yep, these two equations are the same, just with things moved around. I have all the x's and y's on the left-hand side, and I have some constant on the right-hand side. I'm going to factor a little bit. I'm going to take the x squared out of these two terms. So I'm going to have an x squared times some number. So x squared times c squared, and x squared times negative a squared. So we have c squared minus a squared, which is x squared. And then over here, we just have a squared, y squared. And on the right-hand side, we can factor out an a squared, and we're going to have a c squared minus a squared. All right, things are looking good. All right, I am going to divide both sides by the right-hand side's expression so that I have a 1 here. All right, once again, the goal is to make it look like the ellipse and the circle equation. So I'm going to divide everything by a squared. I'm actually going to do it. A squared, c squared minus a squared. I'm going to divide this thing by a squared, c squared minus a squared. Oop. And I'm going to divide this guy by a squared, c squared minus a squared. And things cancel. All right, what cancels? This goes away. Right? These go away. Right? Both of these go away. Becomes 1. That was the goal. And our final equation is x squared over a squared minus y squared over c squared minus a squared. All right? This is the hyperbola equation. This is the hyperbola in its standard form, in what we call its vertex form. The vertex is hiding here somewhere. But before we proceed and look at the variations on this formula, all right, what if it's y squared minus x squared, so on and so forth? What if we have a vertex that is, sorry, not a vertex, a center that is not at the origin? Before we look at those, let's make more sense of this c squared minus a squared value. What is that geometrically? What is c squared minus a squared? What is c squared minus a squared? That value is screaming, to me at least, the Pythagorean theorem. Right? Where c is the hypotenuse. So we have this length c right here. And we have this length a right here. Right? Can we create a triangle that has a leg a and a hypotenuse c? Well, let's do that. All right. I want some point up here. So that A is a leg, I have some other leg, and I have a length C. So what are the points that are all equidistant? What are the points that are all equidistant from E with the length C? That would be a circle. So let's go ahead and make ourselves a circle. Let's stop at B. And let's take the length, let's take this point here, D, and extend it up until we reach this circle. All right, we have this point here and this hypotenuse here in this right triangle. That is going to be the length C. Okay, this is also the length C. Okay, so we have this right triangle here. And then now that we have this right triangle, what is c squared minus a squared? C squared minus a squared is going to be this length right here. This length right here is c squared minus a squared, which would be reasonable. A with a hypotenuse c, let's just go ahead and call this b squared. All right, so c squared minus a squared, c squared minus a squared is equal to some number squared. We're going to call that b, which is the height of a right triangle that is perpendicular to the transverse axis, starting at the vertex and going up until we have a hypotenuse of c. Sometimes when people review or address the hyperbola, they write the formula instead of c squared minus a squared, they write b squared, where b squared is this length, and they often draw it on the axis, the axis of symmetry. They call it b. Let me fix that. This should be the square root, and the square root, so that's just b. Sorry about that. So this length here is b, and what we call this, what we call 2b actually. Let me go ahead and draw a second b down here. We call this the conjugate axis. With that said, I want to look at one other interpretation of this value c squared minus a squared, this value b squared, this value b specifically, and that is, let's look at this formula. So the formula of a hyperbola now is x squared divided by a squared minus y squared divided by c squared minus a squared, which is b squared, which is equal to 1. All right, so we have this formula. What I'm going to do is I'm going to look at what happens to y as x goes to infinity. So we want to look at the limit of this as x goes to infinity. Right, what is that? So let's go ahead and play around with this thing, get it into the form y equals. So I want to look at the limit as x goes to infinity of y, where y is equal to, we need to solve for that. All right, so let's go ahead and solve for that. So I'm going to move I'm going to move the 1 to the left-hand side and the y squared minus b squared to the right-hand side. So we have y squared, we have a positive y squared over b squared, and that's going to be equal to x squared over a squared minus 1. Let's go ahead and combine these two things. So we're going to have y squared over b squared is equal to x squared minus a squared all over a squared. All right, these two equations are equivalent. Let's continue. We are going to let's multiply both sides by b squared. So we're going to have y squared is equal to b squared over a squared times x squared minus a squared. And then let's square root. So now I'm going to take this to the next page. We have the limit as x goes to infinity of y, which is equal to the limit as x goes to infinity of what is y? It is the square root. All right, the square root of b squared over a squared, that's just going to be b over a. The square root of, sorry, I'm toggling back and forth here, x squared minus a squared. The perils of having finite space on the screen. All right, so we had the limit as x goes to infinity of b over a times the square root of x squared minus a squared. So what is this thing going to be? Well, let's perform some limit tricks. So I'm going to go ahead and factor out an x squared in these two terms here. Sounds a little bit bizarre, but you'll see why in a second. Or you may see right away. We're going to have the square root of, I've factored out an x squared, so I'm going to have 1 minus a squared over x squared. All right, and the reason why I did that is now this term right here, right, as x goes to infinity, this thing, a squared divided by x squared, that's getting super duper small. All right, so 1 minus an infinitesimally small object is going to be 1. So this whole thing is going to be equal to b over a times the square root of x squared, which is going to be the limit as x goes to infinity of b over a, the absolute value of x. And so what is this value b? It is the rise over the run a of the asymptotic behavior of the parabola. I totally just said parabola and I meant hyperbola. Disclaimer, parabolas do not have asymptotes, but the hyperbola do. Let's look at this graphically. Right? As x goes to infinity, the parabola slowly, I keep saying parabola, I'm so sorry. The hyperbola becomes the absolute value of x times b over a. So we're going to have a line with slope b over a, which kind of makes sense. If I go up b, half of what I've now defined as the conjugate axis, and then I go over a, right, I have the slope of what this graph right here is getting closer and closer to. And if I go ahead and make the big, nice X, this branch down here is also approaching b over ax, and then negative b over ax over here. Right? The hyperbola has slant asymptotes, unlike the parabola, the thing I keep saying for some reason. And I guess unlike the ellipse and the circle too, obviously. But we have asymptotes. And once again, to go back to that question, what is b? B is the rise over the run A of the slope of this slant asymptote. So that value b is actually quite important too. It reveals what the hyperbola is doing at x as x gets larger and larger without bound. All right, so to wrap up what I've done here, the formula for a hyperbola is x, and this is for when it's centered at the origin. Let me be clear. X squared divided by a squared. We now understand what the value a represents, minus y squared over c squared minus a squared, or b squared. We understand what this value b means, and that's always going to be equal to the value number 1. There you go. The formula for the hyperbola. All right, let's be clear. There are not just horizontal hyperbolas with branches left and right. We can also have hyperbolas up and down. So we can have variations on the hyperbola formula. Notice the coordinates here. This is just convention, but the length of the transverse axis, the segment with endpoints vertices, the two vertices, that length is still going to be a, which is can be quite confusing sometimes. Right? A is now in terms of a coordinate on the y-axis, and the conjugate axis is going to be horizontal. So the coordinate on the x-axis has a b in it. So this is just convention. All right, really just depends on what textbook or what teacher or what professor you have when it comes to the hyperbola. All right. Notice a few other things that change now that we have a new axis of symmetry, the x-axis. The asymptotic slope of what the hyperbola is approaching as x goes to infinity now has a different slope. Right. This line now is y equals rise a over run b times x. All right. This one over here is going to be y equals negative a over b x. All right, this one right here. All right, so the significance of b now is a little bit different now that we've changed. It's the run, but it is still part of the slope of the asymptotic behavior. The foci are still c away, but once again, now they are on the y-axis because we have this vertical hyperbola. And of course, I haven't said this yet, but we can rotate this thing. We'll look at that later. All right, so we have these new values, and what does this do? I'm not going to derive the formula again. I feel like that might be a waste of time. Feel free to do it yourself. This turns the formula into y squared over a squared minus x squared over b squared is equal to 1. And this is when the transverse axis, I'm going to write this, vertical transverse axis. When I'm graphing a hyperbola, I don't always think about a squared and b squared, their position. What I think about is the number under y squared is the length or the square root of the length that you are going to go in the y direction. And then the b squared, I don't think about b, I just think, oh, it's the number under x is the length I'm going to go in the x direction. And that gets me this little box here, which Mr. Rose likes to call the happy box because it does everything you need. It makes you happy. It gets you the asymptotes, and it gets you the vertices. It gets you the transverse axis and the conjugate axis. I guess it's not perfect. It doesn't give you the foci, but you get the foci because a squared plus b squared is going to be equal to c squared based on that triangle we drew earlier. All right, so this is you're not going to really see it if I write it in yellow. Let me do this. This is the happy box. Whenever you write the word happy, you should throw a little smiley face. The big thing you're looking at is the position of y squared and x squared. So whatever's positive versus negative, that's going to determine whether it's a vertical hyperbola or a vertical transverse axis or a horizontal transverse axis. So if the x squared is first, it's going to be a horizontal. If the y squared is first, or if the y squared is positive, it's going to be a vertical transverse axis. So with that said, I'm about to attempt a example problem. It's gonna be pretty straightforward, but the goal is often given some of the properties of a hyperbola, can you determine the rest and give the graph or give the equation something along those lines. How do I create this hyperbola? Important values are a, b, and c. So normally, somehow you're going to get, you're going to be given two of these values, or you're going to be given enough information to get two of these values, and that'll give you the ability to get the third value. All right, we have the Pythagorean relationship between a, b, and c. So 2 is enough to get the third value. All right, so let's go ahead and do an example. So I want you to graph the hyperbola y squared over 16 minus x squared over 49 is equal to 1. We are in the graphable form already. No need to move things around. You can imagine how I might change this, so you need to get to this form. All right, but let's just evaluate some things. So we have a squared. A squared is equal to 16. Right, so a is going to be equal to 4, and b squared over here is equal to 49. So b is equal to 7. Those lengths are relevant. And we want to get the foci length as well. So we're going to take advantage of that Pythagorean relationship. A squared plus b squared equals c squared. So we already have a squared and b squared. 16 plus 49, that's going to be equal to c squared. C squared is equal to, what is that going to be, 65. So C is equal to the square root of 65. All right. So we have A, we have B, we have C. We need to evaluate whether this is going to have a vertical or horizontal transverse axis. And I believe this is going to have a vertical transverse axis because that y squared is the leading term. I like to think vertical transverse axis because y is often vertical. All right, so we are going to go for units in the y direction. So let me go ahead and give myself a new color. We're going to go 4 units. Probably should give myself some ticks. 1, 2, 3, 4. We are ultimately going to go 7 in the horizontal direction. So let me get that too. 1, 2, 3, 4, 5, 6, 7. And the square root of 65 is just bigger than 8. So we do have a vertical transverse axis, so the foci will be on the y-axis, so we need to go 8, a little bit more than 8 in the y direction. So 1, 2, 3, 4, 5, 6, 7, 8, and we're going to be like 8.1-ish. So I need to go up to 9, 2, 3, 4, 5, 6, 7, 8, 9. Over here, 1, 2, 3, 4, 5, 6, 7. Let me go ahead and graph all of these relevant points. So I'm going to graph 4, 1, 2, 3, 4. And then down here at -4. All right, that is my A value. That is how far I'm going. That is my my vertex. My foci are going to be 8 and a bit, 8 and some change. All right, so this is, I'm going to go ahead and label this foci 1. I'll label this foci 2 arbitrarily. This is my vertex 1. This is my vertex 2. And then I'm going to go ahead and get that B value graphed on here as well. 1, 2, 3, 4, 5, 6, 7. Because that's going to help me get that happy box to get my asymptotes. All right, so since this is vertical, my my asymptote slope is going to be A over B. All right, so I'm going to go ahead and graph that box. Stop there. Go up. It's a little bit sloppy, but that's all right. Make it as neat as possible. We are human. Right, there is my happy box. And then I'm going to go ahead and graph my asymptotes because those are key in making my my hyperbola pretty and pretty accurate. Pretty accurate. All right. As my hyperbola goes, as x goes towards infinity and negative infinity, I'm going to be approaching these lines. So let's go ahead and draw that hyperbola now. This is one branch, and this is the other branch. And I'm going to try to fill these in a little bit. I know I'm doing dotted lines, which isn't the best, but all right. And the distance, what is an asymptote? The distance between the hyperbola and this dotted red line is going to get smaller and smaller, as small as you want. Depending on how far you go out. All right, so cool. There is my hyperbola. Y squared over 16 minus x squared over 49 is equal to 1. So I am going to move on. I'm only going to do one example where we are centered at the origin. I want to do one where we're not centered at the origin, but I will leave the other problems. There are lots of different types of problems I can give you that involve graphing and determining a hyperbola. Lots of different information I could give you. I could tell you about the latus rectum, which is the latus recti, which are the segments that go through the focus, but are perpendicular to the transverse axis. The segment that connects from the hyperbola through the focus, perpendicular to the transverse axis. I could give you that, and you'd be able to determine the hyperbola as well. Lots of different questions. I could give you the eccentricity of the hyperbola, but I am going to stop here. I'm just going to do a basic one. I'll leave that stuff for you guys to play around with. Let's go ahead and look at a hyperbola with non-zero, zero center. So let's jump into an example. I want you to graph this thing. 25x squared minus 9y squared minus 100x minus 72y minus 269 equals 0. And if you've already played around with the ellipse and the circle equations, you might know that you need to complete the square. All right, so let's go ahead and do that. And then once we are in that form, once we've completed the square, we'll be seconds away from the hyperbola form. And then we'll be able to determine A, B, C, H, and K, and we will be golden. We will have our graph. So I'm going to rearrange this. I'm going to write this as 25x squared minus 100x. I'm going to group terms. I'm going to minus 9y squared minus 72y. And I'm going to move that 269 to the right-hand side. Cool. Now I'm going to factor. All right, because I want to complete the square. All right, so I'm going to take out that 25, and then I'm going to have, what is that, minus 4x. All right, I'm going to add something there. All right, I'm going to factor out a negative 9 so I can deal with positive numbers. I'm going to have a y squared, and then 9 times 8 is 72, so minus 8. Y, I think it may have, this needs to be a plus. Factoring is difficult. I like to say factoring is difficult, but checking your answer is not. So negative 9y squared, negative 9y squared, negative 9 times 8 is negative 72y. Beautiful. All right, I'm going to have a term there, and that's equal to, I'm running out of room, 269. Cool. All right, so what do I need to add here? Change up the color. I need to add b divided by 2 squared. So 4 divided by 2, 2 squared, 4. I need to add a 4 there. All right. I have added to the left-hand side of this equation, so I need to add to the right-hand side. How much have I added? Not 4, but 25 times 4. So I've added 100 to the left-hand side, so I need to add 100 to the right-hand side. Over here, I have running out of room, but 8 divided by 2 is 4, squared is 16. And so I've added not 16, but negative 9 times 16. Negative 144 to the left-hand side. So I need to add negative 144 to the right-hand side. Be careful there. We're not adding 16. We're not adding 4. We're adding 25 times 4. Negative 9 times 16. All right. And with that said, we've now completed the square. I'm going to keep the color green. We have 25 x minus 2 quantity squared. All right, that's just completing the square. Minus 9. We have y plus, what is that, 4 squared, and that's all going to be equal to 269 plus 100 minus 144, which is a nice round 225. And then we are now in completed square form. Let's go ahead and get it in hyperbola form. We need this number to be a 1. Let's divide both sides by 225. And we are going to get x minus 2 quantity squared divided by 9. We are going to get y plus 4 squared divided by 25. And 225 divided by 225 is 1. We are now in a hyperbola form. We are in standard form. We are in graphable form. So we just need to extract from this the relevant values. X is the leading term. It's the non-negative term. So we are going to have a horizontal transverse axis, and we're going to be going 3 in that direction to get the vertex. We're going to be going 5 in the y direction to get the endpoints of the the conjugate axis, and then we need to find the focus points still. And we are also going to have a shifted center. We are going to have 2, -4 as our center. All right, I'm going to go ahead and write all those relevant values down. So we have the center at, 2, -4. We have an A value of 3. We have a B value of 5. Using the Pythagorean theorem, 3 squared plus 5 squared, all square rooted, we're going to get 25 plus 9, that's 34, which is a little bit less than 6. All right, the 6 squared is 36. And then let's go ahead and graph this thing. So let's go ahead and get that center first. So I'm going to need a few tick marks. I'm going to go ahead and get my center before I start adding all the rest of the tick marks. All right, so my center is right there. And then I need to go in the horizontal, the x direction 3. So 2, 3, 4, 5. And then in the other direction, 1, 2, 3. That is going to be my vertices. All right, let me actually bring that one up a little bit. Cool. All right, so V1, V2. And then, let's see, I'm going to be going in the vertical direction, y, 5, for my the endpoints of my conjugate axis. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, those points right here and here are simply to help me get that happy box to draw my asymptotes accurately. And then this is a x squared minus y squared hyperbola. So my transverse axis is horizontal. So my foci are going to be an extension from that. They're going to be a little bit less than 6 away. So 1, 2, 3, 4, 5, 6, a little bit less. All right, in the other direction as well. 1, 2, 3, 4, 5, 6, a little bit less. Cool, those are my foci. Next thing I'm going to do is I'm going to go ahead and graph my, my happy box. And I'm going to go ahead and change the color up. I don't know, what are you guys' favorite color? I haven't said this, but put your answer in the comment section. Don't forget to like and subscribe. All right, this is going to go up this way. Same thing over here. All right, if you want, you can write down the equation of these things. Y is equal to negative. This is going to be the B value over the A value. So we're going to have a 5 over 3. 5, this is negative 5 over 3. But we have a point slope thing going on here. So I'm actually going to have to erase that Y and then do a Y. There we go. Y minus a point. So I'm just going to use the center. 2, -4. So Y minus -4, Y plus 4 times slope x minus 2. All right, there's that one. And then the other one is going to be Y plus 4 is equal to positive 5 divided by 3, x minus 2. Cool. So there's my, my equations of the asymptotes. Those aren't really what I care about, though. My goal was to graph this hyperbola, which I'm going to do in purple. We have the vertex, and then we are approaching these asymptotes, right? Infinitesimally close as x goes to positive or negative infinity. A little bit bad there at the top on the left, but I'll get over it. Hopefully you guys will. I want this kind of be a little bit more symmetric, so I'm going to make it a little bit more symmetric. Make this go up this far. All right, I'm like literally on the line. That shouldn't be the case, but whatever. All right, so there he is. That purple thing is the hyperbola with all of its attributes. Its transverse axis, its conjugate axis, its foci, its vertices, its center. And it has been shifted, and it was given in this nasty form that we turned into the correct form. So that is your hyperbola. All right, once again, there's other types of problems I could give you here, but I'm going to keep it simple. And with that said, I am going to actually go ahead and wrap this video up. let me jump back to the first slide. We looked at the hyperbola. We looked at the definition. We looked at the formula. We looked at the variations on the formula, if it has a vertical or horizontal transverse axis, and if that center has been shifted. And in doing that, we looked at some examples. So the rest is for you guys to figure out. I encourage you to learn as much about this shape as possible. Like, don't stop at what I expect. Go a little bit further. But I will close it out here. So have a good day.